Hello, everybody. This is section 4.7, the lecture 4, section 4.7, applied optimization problems. So, and in this section, what we're going to be doing is we're going to be taking a step outside of mathematics and going into some of the physical sciences to do a little bit of work there. Okay. One of the most useful things about calculus is that it allows us to do a fair amount of stuff for other subjects. Okay, in this case, we're going to be doing optimizations. Okay, how can we optimize? How can we optimize a specific scenario to squeeze out the very best possible? Okay, so this is not only used in physical science. This is actually used in a lot of the social sciences. So economics, psychology. Okay, so in economics, how can we squeeze out the maximum profit? How can we squeeze out the very last dollar, right? In order for us to make the most money. Okay, so that's what we're going to do in this section. What I want to do first is I want to go through, like I've mentioned from the beginning of the class, there is a textbook for this course. Okay, you don't have to read it. It's got some good examples in there. It doesn't go off of what it doesn't go too far off of what I'm saying, and I'm not going too far of what it's saying. So if it's there if you want to read it. Okay, what I want to go through first is there's a general strategy for solving optimization problems, and this one's from the book. Okay, it's got 6 steps. 1, 2, 3, 4, 5, 6. So I want to cover the 6 steps really quick as it's done in the book. Okay, so step 1 is, if possible, draw a figure and introduce all of your variables. Okay, so make the picture nice and big, introduce all your variables, call the stuff x, y, call lengths and heights, whatever you need to do, right? Draw a picture and label everything, right? Step 2 is determine what quantity needs to be optimized, right? And for what range of the other variables present, okay? So if you need to optimize a length, right, make sure you can identify that this L, this length is the thing that I'm going to be optimizing, okay? Step 3, write a formula for the quantity that needs to be optimized in terms of the variable. So within our problems, within our scenarios, there's going to be a variable, there's going to be something that we need to optimize, whether it be maximized or minimized, one of the two. Okay, make sure you can identify whatever that is. Okay, step 4, write out any equations that may be possible constraints in terms of the independent variable. So what I mean by this is, since we're optimizing, right, we're trying to find the maximum or the minimum of something, there is going to be something that is going to be constraining in our problem. So we're going to have like an infinite amount of something, right? But only a finite amount of something else. Okay. Make sure you can identify those, write out any of the equations for them, right? That may be possible constraints in terms of those independent variables. Okay. For 5, identify the domain of consideration for the functions for step 3 and 4. So if you're going to be working with equations, right? This is basically saying, if you're messing with lengths, you can't have negative lengths. So basically, you're not going to have anything where the length is less than 0, right? That's basically it. It's not much, okay? And problem 6, this is what's going to use the stuff that we learned from section 4.3, 4.4, 4.5 in order to solve this, in order to do part 6. We are going to try to find required extrema, whether it be maximums or minimums. Okay, so once we do 1, 2, 3, 4, 5, 6 is basically finding the extrema, finding whether you have a maximum or a minimum and what it is. Okay, so like I mentioned, this is the problem solving strategy from the textbook. It's cool and all, but I think this problem solving strategy, the way that this is worded and the way that it's presented, this is the problem solving strategy that's only really good for section 4.7. Okay, so what I have below is a separate problem solving strategy that I think is much more useful for everything outside of this class. Okay, this is a much more general problem solving strategy, which will not only help you out just in this math course, but it'll help you out outside of math. So in your physics class, in your economics class, in your sociology class, in your chemistry class, okay? The name for this problem solving strategy, you guys can go and read it up if you want to. It's called Polya's heuristic. So this guy, George Polya, he passed away, I believe, late 80s, 1980s. He was a professor at Stanford for like 40 years. He's got quite a few names, quite a few theorems to his name. In mathematics, you know you're the bee's knees if you have theorems written about yourself. So he's got a couple, okay? And in his proving these highly mathematical theorems and really complex ideas, he wrote a book about how to solve a problem. That's actually that's the title of the book, How to Solve the Problem, right? And in this book, he describes this problem-solving process, okay? So I'm gonna go through it really quick. This is the thing. This is the thing that he wrote down, okay? And his book is just how to apply it to different problems that he's seen, okay? So let me go through it really quick. Step one only has you just understand the problem. That's step one, just understand the problem. So read the problem carefully until you understand it enough so that you can repeat it in your own words, okay? Make sure that you can identify any knowns and unknowns as well as any conditions or constraints that you may have within the problem itself, okay? So this is just basically, if you need to, read it, reread it again, right? And make sure that you can identify every single little bit of the problem, okay? That's step one. Step two is devising a plan, okay? Notice how I have highlighted there, no math, okay? We're not doing math yet. Like, we're not doing the bona fide algebra or arithmetic at all for the problem yet, okay? This is just devising a plan. So this means, how are you going to go about solving this problem? Can you provide some sort of step-by-step, right? We're not plugging in yet. We're not, there's no math, no arithmetic, no algebra involved yet, no plug and chug. Just, can you provide me a step-by-step to get to an answer, right? This is where you would draw a picture if you needed it, right? Introduce any extra notation. So if you had to call something a length and another thing a width, this is where you would put it in, right? Write out any formulas that you have to remind you if required, right? So if we liken this to a football game, right? This is where we're drawing out the play. This is where we're drawing out the play. We're on the sidelines, we're in the huddle. This is what's gonna happen, right? Okay, step three is actually carry out the plan. Step three is actually carry out the plan. So in step two, you figured out some sort of game plan, right? You figured out some sort of play that you're gonna do in order to solve this, right? Now you go in and do the nitty-gritty stuff. You plug in values, you do everything that you need to get the work out, right? So this is where, now that you have a game plan, right? Now do it, right? Stick to the game plan as best you can. If something happens that throws you a little off, that's fine, but keep going, right? Make sure you review the arithmetic correctly and make sure everything's working out right. This is where you're actually like concentrating on getting sort of, the nitpicky stuff correct, right? And then the last step is review and extend, okay? So after step 1, 2, and 3, you should have a numerical answer for yourself, right? Step 4 will be checking that the numerical answer, right, has the right units and that you can relate it back to your problem, the original question itself, right? Did you answer it? Is there something that didn't look right? Let me double check my answer. Let me make sure my answer is correct, right? So this is basically, the spot where, if you're doing a problem and the answer ends up being peanut butter, something went wrong, right? You have to go back and double check it. Maybe I did something wrong. Maybe my calculation didn't look right, okay? So this is Polya's heuristic. And like I said, I think it's much more useful than the one that's above. okay? Because the one that's above is only good for section 4.7. Polia's heuristic is good outside of this math class, okay? So what I want to do now is I want to do a couple of examples using these problem-solving processes, okay? And for just so I can get the idea straight, I'm only going to be using the second one, the one on the bottom. You can go ahead and use both. Both are perfectly fine, okay? I believe the videos in your homeworks do the top one, okay? But I'm going to do the second one just so that people can see how this is working out, okay? All right, so let's jump into this. So I have an old farmer that needs to enclose a large piece of rectangular pasture for his cows, right? One of the sides will already be enclosed by a cliff, okay? So he only needs to deploy a fence on the remaining 3 sides, but the farmer only has 200 feet of fencing at his disposal, okay? What is the maximum area that the farmer can enclose for his cows? All right, so number one, like I said, step one from Polia's heuristic is understanding the problem, right? So what we have here is, this farmer, he's got a bunch of cows, right? We only need to take care of 3 sides. So the fence that we need to put up is on 3 sides because one of the sides is enclosed by a cliff. So one side doesn't need a fence, okay? And we have a constraint, right? That constraint is he only has 200 feet of fencing at his disposal, okay? And the whole problem is asking us to maximize the area for his cows, okay? So this is the thing that we're trying to find, right? What is the maximum area, okay? All right, so step one is done. This one, like I said, this one's just the reading and sort of absorbing what the problem is saying, right? So this one's done. This one tends to not have too much work. Step two, though. Now we're going to go ahead and do a game plan. We're going to devise a game plan, right? So let's go ahead and draw a picture, right? So I'm going to go ahead and here's make this a little thicker like that, you know? Here's our cliff, right? There's our cliff. And let's draw in now our rectangular thing, right? Okay, so since this is rectangular, right, I'm going to have a length here, and I'm going to have a width here. I don't know what those things are, right? Okay, but we have a couple things, right? And that means that this is a length as well, right? Okay. So let's go ahead and start writing out some of the equations and stuff that we need for this particular problem, right? We need to maximize an area, right? So A is the area for this rectangle, right, is going to be my length times my width. So I know that this is the thing I need to maximize somehow, right? Okay. I also know that the farmer only has 200 feet of fencing at his disposal. So then that means if I put, if I'm looking at my drawing here, right, that means that my 2 lengths plus my width has to equal 200 feet, right? So this right here, the second equation that I wrote down, this is part of my constraint. I'm being constrained by the amount of fencing that I have, okay? So this right here mostly gives us our game plan. So what we have to do now, right, is we have to maximize this right here, right, using this constraint. Okay. So optimizing that area means we're going to have to do calculus, right? So I'm going to do optimizing. ING is finding a max or a min, right? So that means we're going to need to use calculus on A. We need to use calculus on the area equation, right? So that's exactly what I'm going to do. I have the constraint equation, okay? So then therefore, I can say, right, that my W is 200 minus 2L. So I've restated this equation for my constraint, right? Equal. You make that equal a little bit more pronounced. There we go. Okay. Now that we have this, right, we have a plan now that we need to follow. We want to optimize our area based off of this constraint that's right here. That's been rewritten. Okay. So then now is step 3. We're going to go ahead and carry out our plan. Okay. So we know that W is this. My A is that. So I'm going to do A is equal to length times width. I know what my width is. So it's going to be length times 200 minus 2 times length. So then therefore, now I have A solely in a variable of L is equal to L times 200 minus 2L, 200L minus 2L squared. So remember how we said it in step 2, we want to maximize or minimize this area right here, right? We know from section 4.3, 4.4, 4.5, that the maximums for stuff happen at critical points and minimums for stuff happen at critical points, right? So and that means I get to take the derivative of this area function. So A prime of L is going to be 200 minus 4L. And we need to set this equal to 0. Solving this out, we get that L is 50. Okay. So now comes step 4. We need to review our work and extend it. Okay. In particular, we need to review our work in particular. So we have a numerical answer. We have this answer right here. L is equal to 50. Right? That is the length. I'm now going to put units in feet, right? This is the length that maximizes the area. That's what we just found. Okay. So then step 4 is asking us, what is the maximum area, right? We need to review our work. So then the area, let's take a step back. We have the length, we need the width, right? So the width, actually, we're not doing step 4 yet. We're still computing stuff, haha. So the width is going to be, we're going to use our original equation from the constraint, 200 minus 2 times 50. And that is going to be 2 times 1, 50 is 100, it's going to be 100. So my length is equal to 50. My width is equal to 100. Okay. So then my area is going to be 50 times 100 is 5,000. Okay. Now we get to do our review and extend. So our answer now altogether is that the maximum area, right, is 5,000 feet squared. And we got that from right here. Does that make sense? So let's go ahead and take stock of what we did here, right? So at the very beginning, right, we had to understand the problem, see what it was that it was asking us, right? Step two, we need to figure out a game plan, right? So from step two, we figured out that we needed to maximize that equation given this constraint, okay? Step three, we actually went through it. So in step two, we decided, we found our equations and we needed to use calculus. And that's what we did. And we got our numerical answer, right? And then finally for step four, we end up sort of summarizing our work into this nice phrase right here. Okay. There it is. This is optimization. You guys see how useful this is? So I did it with some cows and a farmer, right? I don't know if a farmer would do this, but I mean, the idea is sound. Okay. Okay. What I want to do is I want to do one a little bit more complicated in as an example. This happens a lot in whenever you need to mess with trajectories, okay, where you need to minimize a distance, right? So which point on the graph of that right there are closest to the point 1, 2? So I give you guys a graph for it. So this thing right here is my f of x, okay? And that's my point 1, 2. We want to find the points that are closest to it, right? So if we just sort of eyeball it for now, right? If we just sort of eyeball it, it looks like maybe about right there, about right there. So it looks like those two are the closest. If we start moving, if we start going, any farther away from here, right? That distance is going to get bigger, right? So it looks like it'd be right there. So again, we've already got the idea here. We're trying to minimize the distance. We're trying to find the closest point, right? So that's exactly what we're going to do. So step one is done. We sort of talked it out. We want to minimize the distance, right, between 1, 2 and the rest of the graph. What point is the closest, right? Okay. Step two, we're going to devise a plan now, right? So we know what we need to do. We need to minimize that distance, minimize the distance. Okay. One of the equations that I'm going to have to pull out from your geometry days is this one. Let's say you have let's say you had a point x1, y1, and another point x2, y2, right? Then the distance between the 2 points is going to be the square root. This is basically a Pythagorean theorem, okay? X1 minus x2 squared plus y1 minus y2 squared. So this is an equation from maybe high school geometry that if you have 2 points, right, an x1, y1, x2, y2, okay, the distance between those 2 points is given by this equation right here. Okay, so somehow, some way, right, we need to minimize this equation. Okay, now the question now becomes, what's our constraint, right? The constraint becomes this point right here, right? The constraint becomes that equation right there, or that point, sorry, right there, right? So what I'm going to do now is I'm going to do this. We know the coordinates of this blue point. I'm going to grab a rando point here, right? So I'm going to say this. This is going to be my x1, y1, right? And this is going to be my x2, comma, y2. Make sense? In general, for a graph of this thing, right? This is going to be whatever x is, comma, whatever the function value at that point is as well. Does that make sense? So I can rewrite this as this now. x1, comma, y1 is going to be this point right here. It's going to be the 1, comma, 2, right? x2, comma, y2. This is the point that's on the graph. So this is going to be an x, comma, f of x, which then turns into x, comma, I know what the function is, minus x minus 1 squared plus 4. Now I can use this in here because I have x's, x1s, y1s, x2s, and y2s in here, right? I can use both of these coordinates, this and this, right, in the distance equation, and hopefully, right, get an equation which just has x's in it. Okay, so that's exactly what I'm going to do here. So I'm going to do, I'm just going to go ahead and write it out. So my d is going to be the square root, nice and big, 1 minus x squared, okay, plus y1 minus y2. So that's going to be 2 minus x minus 1, and that's supposed to be in parentheses there, squared plus 4. And now I can make this nice and tiny. There we go. Bam. Okay, and look what we have now. Everything is in the variable x. So now we have d of x is equal to this equation right here. Okay. So now I have a distance equation between our blue point and any other point that is on the graph. Okay. So now, hopefully now that we have this, right? And I forgot a square up here, square. Now that we have this, we can do, we can figure out a game plan. We need to take the derivative of this, right? And we are looking for the closest point. So that means we need to find the minimum here, right? Maximums or minimums are done by finding the critical values. So that's all we need to do. We're looking for critical values now, right? Do the very best that we can for critical values for this thing, okay? So here we go. Step 3 now. Now we get to do what we came here to do, right? So I need d prime of x. I'm going to rewrite, let me actually write regular d first. I'm going to rewrite this. It's going to be 1 minus x squared plus 2 minus, I'm going to go ahead and clean this up a little bit, plus x minus 1 squared minus 4 squared, and then all of this to the 1/2. Okay, I'm going to make it a little nicer again. 1 minus x squared plus, so 2 minus 4, that's going to be minus 2. So this is going to now be x minus 1 squared minus 2 squared to the 1/2. Now I'm going to go ahead and take the derivative. So d prime of x is going to be equal to, okay, this is going to require a chain rule, right? So it's going to be 1/2 times the stuff in here. So it's going to be 1 minus x squared plus x minus 1 squared minus 2. So the minus 1/2, okay, times 2, 1 minus x times negative 1. Okay, let me write it out first. Plus 2 x minus 1 squared minus 2 times 2 x minus 1. Okay, so notice how, let me explain what happened here, right? This portion right here is the very beginning portion of the chain rule, right? It's the derivative of the outside leaving the inside by itself. And then it's supposed to be times the derivative of the inside, the derivative of this stuff in here. Okay, so let's break that down now. So the derivative of this, you drop down the 2, right? Times the thing by itself, times the derivative of the inside. So that derivative is this. Okay, plus the derivative of this. And I forgot to square something here. Look at me go. There we go. Okay, the derivative of this thing in the pink, right? That's another chain rule. So I get to drop this down, leaving the inside by itself, right? Times the derivative of the inside. So it's going to be 2 drops times x minus 1 times 1. So this is the derivative of that second half, the second portion of the inside. Okay. Okay. This now reduces to 1/2. I'm going to rewrite this all again. 1 minus x quantity squared plus x minus 1 squared minus 2 squared to the 1/2, right? And if you do all of this out, okay, this should reduce down to 4x cubed minus 12x squared plus 6x plus 2. Okay, and this is supposed to be a minus 1 now. So I'm going to rewrite this now to make it look nice and neat. 4x cubed minus 12x squared plus 6x plus 2 all over. And I should put that times 1/2 up front. All over the square root of 1 minus x squared plus x minus 1 squared minus 2. Make this look a little nicer here. It's a little sloppy. 1/2 times that. Okay. So now we're in step 3 here now, right? So we were looking for critical values. So that means that this thing has got to be equal to 0. that thing has got to be equal to 0. So what I'm going to do is I'm going to open up Desmos, and this is perfectly fine for you to do. Okay. The first argument I need to make, right, is remember the argument that I was making in the previous sections, right? That if I have a fraction and that is equal to 0, right, then that means solely the top has got to be equal to 0. So therefore, right, 4x cubed that's got to be equal to 0. So in this case, the lost my train of thought. So in this case, this is a very difficult thing to factor out. I mean, you can if you wanted to. I'm going to go ahead and do it by Desmos. Okay. I'm going to go ahead and do it by Desmos. Okay. So I'm going to actually write down here so that people don't get lost here. Okay. I'm going to do a double window thing here. Bam, bam. I'm going to find out when that thing is equal to 0. So 4x third minus 12x squared plus 6x plus 2. I need to find out when it's equal to 0. There's 3 points there. Let me make it. There we go. There's 3 points. There's that one, and that one. Got it? So then by Desmos, I got, yeah, that's good. X is equal to negative 0.225. X is equal to 1, and X is equal to 2.225. Right? So now I've got my values, right? I'm going to actually switch these to A's so I can do a computation with them. Hopefully you guys are using Desmos this way too. And actually I need the original equation. Aha. So I'm going to go back up here. I'm going to use my original equation. So this is the square root. And I'm going to need to use the A's. Here we go. 1 minus A squared. I'm going to use the shortened version. This one right here. So then plus x minus, or a minus, oops, a minus 1 squared minus 2. Okay, so let me actually make this a little bigger. There we go. Okay, and I'm going to find 3 values. Okay, so I'm going to go ahead and actually write them down right here next to these. Negative 0.225. So I'm going to go ahead and I'm going to make that the negative, and I get 1.006, 1.006. Okay. When I plug in f of 1, I think we had that already. 1, it's undefined. So answer does not exist. And then finally, f of 2.25, 225, sorry. Let me go ahead and change that 2.225. So I'm gonna go ahead and plug that in here. 1.006. Okay. From our previous section, right, we know that the maximums and the minimums have to happen at these critical values, right? And it just so happens that we found the distance that does them. Okay, so I'm gonna go ahead and do this here. The original question, so this is the end of part 3, I should write that in. So for 4, right? To the point 1 comma 2 are x equal the negative 0.225, right? And x equal 2.225. Okay, this is our final answer right here. So remember what we were trying to do. We were trying to find the points, right, where the distance to the point 1 comma 2 is the smallest, but it's got to be on that graph. It has to be on that f of x. And that's exactly what we did. The 2 points that will do it are those two right there. X equal negative 0.225 and x equal positive 2.225. So now let's go back up here, right? I'm going to draw it in with the orange now. You take a look, it's pretty much right where we guessed it. So remember how we guessed it, it'd be like maybe about right there. That'd be the closest, right? And then same thing over this way. Pretty darn good, right? Okay. And I believe that is it. I gave you guys some hard ones for examples so you guys can sort of run through the process, right? Will you ever do something that difficult? I would say very rarely. So it's good to know how to do them, okay? These are a little bit much more straightforward, okay? The ones that you're gonna see in your homework are much more straightforward as well, okay? If there's any questions about how to do these, if you're getting stuck on whatever, right? Come by my come by my lab hours, show up in my Zoom room, send me an email, send me a discussion post somehow, somewhere, and I'll take a look at them, okay? Besides that, study hard, and I'll see you guys around.